Hello chemistry citizens, welcome back. We're going to talk about the mass lab that we did. There were 6 parts to this mass lab, and each part kind of had its own ideas, and hopefully you did it and remember what you did and understood it. So we're going to go over the understanding part. Hopefully it all makes sense and how the molecules and how the chemistry is actually working. So the first part was a steel wool. So part number 1, steel wool. In this part, what you basically did is you took a chunk of steel wool, you scrunched it up into a little ball, weighed it on a scale, pulled it apart, or stretched it out, or whatever you want to call it, and then re-weighed it. Majority of the people got a negative change in mass. The question is why? Why did they get a negative change in mass? Because when you pulled it apart, there was steel that either stuck to your fingers or broke off and fell onto the lab table or the desktop, whichever one it was. So that's why you got a negative change in mass. But in an ideal situation where nothing fell apart, you should get a 0 change in mass. So make sure you can account for why most people got a negative change in mass. So let's draw what these molecules are doing and how they look. So in the compressed form, the steel wool, which we'll represent with circles, was very, very close to each other. Something like this. All right? So now, once we stretched it apart, pulled it apart, we didn't change these molecules. What we did is just increase the space between them. So now we have molecules that are further apart. You didn't change, you didn't make a new chemical or compound, you just made them further apart. So remember, these molecules are moving, not a lot, but they are moving. Remember, absolute 0 is the only time that these things don't move, these molecules don't move. So the big difference between stretching them apart is that, one, it takes up more volume, all right? And that's just all you needed to realize for that part, was that we didn't change anything, we didn't make a new compound, but the molecules are moving a little bit differently, are behaving a little differently because we stretched it out. And make sure you realize why people lost mass, when ideally, in an ideal world without any surroundings, you should have had a 0 change. Part 2 was ice and water. What you did in this little part here is you basically took ice, a couple ice chunks, you weighed it in a vial, you let it melt, turned to a liquid form, and then you re-weighed it. So this is kind of a build-off of the first part. So what happened in this part, in terms of molecules, is the solid form of ice, which we'll represent, say, with molecule, we'll just draw X's. The molecules were close. So in a solid form, molecules are very close to each other. Remember, they're moving, but they're not moving a lot. All right? And then in liquid form, really, all you did was change states. So the difference between a solid and a liquid is that the molecules are now farther apart. They take up more space, so they increase their volume. All right, so molecules are moving, but they're just farther apart. We didn't make a chemical change. How do we know we didn't make a chemical change? Because there wasn't one of the 4 signs of a chemical reaction, which we talked about in the flame demo video. So if you don't know what the 4 signs of a chemical reaction is, make sure you go back to that flame demo video, and it should explain that for you. The third part of this lab was the mass of a precipitate. All right, so what did you do in this lab? Well, basically what you did is you took 2 clear substances, and you filled up 2 different vials or test tubes, and you weighed them together. Then you poured one of them into the other, and so you had an empty one and almost a full one. And when you mixed them together, you should have got it. You should have seen a little chemical change happen, and you should have re-weighed them, both the test tubes, and you should have seen the difference, if there was any. So, what is a precipitate? A precipitate is when you take liquids and you make a solid. So in this part of the lab, what we did is we took 2 clear liquids and we made a white solid. It should have got cloudy, it should have turned white, and in that solid, it was a color change, and a precipitate got formed, which are 2 signs of a chemical reaction. So that's how we know we had new particles or new molecules made. So how would we represent that in a visual manner? So before, let's say we had, here's one of the compounds, which we'll represent with X. And this is the compound that had the Ca in it, calcium in it. I believe it was calcium nitrate. And then we had another compound over here, which had sodium in it, and I believe it was sodium carbonate. All right, so these, we weighed them, and then when we mix them together, you got a white substance. So that means we got a new molecule. So now we don't have these X's and O's anymore. Now we have, say, triangles, which could be one thing, and then we also have squares. So we made two new compounds. One was a little more evident than the other, like the white stuff. You saw the white stuff; it was pretty evident. And the other stuff was actually a different type of salt, or even a different type of solid that was still soluble in the water, which you couldn't see. All right. You should have, in this one, you should have got a close to zero change in mass. All right. And the reason why some people may not have gotten a zero change in mass, they could have spilled, maybe they weren't careful, things like that. But the change in mass should have been close to zero on this one. Let's talk about the fourth part now. In the fourth part of this mass lab, you burned the steel wool from part 1. All right, so you took a chunk of steel wool, you weighed it, then after you weighed it, then you took it and you put it into a Bunsen burner and burned it, and it should have glowed and heated and all that stuff, and then it probably smelled wonderful too. And then you guys should have reweighed it once it cooled down. So the particles that we see, or we should have saw in this, is before the steel wool was just like this. Okay, all scrunched together in a solid form, very close together. That's going to be our steel wool. So here is our wool. All right, make sure you spell steel wool right. And then what we did is we burned it. So we put a Bunsen burner to it. All right, so we hit it with a flame. All right, and what are we essentially hitting with it when we're talking about a flame? Well, what we're really worried about and what we really want to concentrate on, there's a bunch of things in a flame, but the one thing we want to worry about is the oxygen. So we'll represent the oxygen with X. So the X is the oxygen from the Bunsen burner. Now, when we did this, we saw a color change. We saw orange color. It got warm, which is an energy change. So we know a chemical change took place. So now, on the steel wool, there might have been some steel wool left over that we didn't burn or that didn't get hit with oxygen. So this is maybe the stuff that didn't get hit with a flame, but in the rest of it, you got a new compound. So let's put that with triangles. So say we burned all this stuff, and we got triangles over here and over here. So it's still a solid form. This should have been kind of a darker color, maybe even a red color, depends how long you burned it for. So now here's the steel wool that wasn't heated, but now here's the steel wool that was. And now this is now steel wool, which is iron, and oxygen. This is iron oxide. All right, iron oxide is also known as rust. So we rusted the steel wool. So how do we know we made a new compound? Because we saw two of the signs of the reactions. We saw color change, and it got warm, so therefore is there energy change. What you should have got for a number in this, you should have got somewhere close to a positive change. Some larger than others, depending on how long you heated, but it should have been a positive change because the thing that we did to this experiment is we added oxygen to it. So when you add atoms to the iron, it should weigh more because you're adding more mass to it. All right, so you should have got a positive change in mass from start to finish. The fifth part